0.999 ... In mathematics, 0.999 ... also denoted 0.9 repeating, is a recurring decimal which is exactly equal to 1. In other words, the symbols 0.9 repeating and 1 represent the same real number. Mathematicians have formulated a number of proofs of this identity, which vary with their level of rigor, preferred development of the real numbers, background assumptions, historical context, and target audience. The equality of 0.9 repeating equals 1 has long been taught in textbooks, and in the last few decades, researchers of mathematics education have studied the reception of this equation among students who often vocally reject the equality. Their reasoning may be based on the expectation that infinitesimal quantities should exist, that arithmetic may be broken, or simply that 0.9 repeating should have a last 9. These ideas are false in the real numbers, as can be proven by explicitly constructing the reals from the rational numbers, and such constructions can also prove that 0.9 repeating equals 1 directly. At the same time, some of the intuitive phenomena can occur in the other number systems. There are even systems in which an object, which can reasonably be called 0.9 repeating, is strictly less than 1. That the number 1 has two decimal expansions is not a peculiarity of the decimal system. The same phenomenon occurs in integer bases other than 10, and mathematicians have also quantified the ways of writing 1 in non-integer bases. Nor is the phenomenon unique to 1. Every terminating decimal expansion has a twin with trailing 9s. In fact, all positional numeral systems contain an infinity of ambiguous numbers. These various identities have been applied to better understand patterns in the decimal expansions of fractions and the structure of a simple fractal, the Cantor set. They also occur in a classic investigation of the infinitude of the entire set of real numbers. Section 1. Digit Manipulation. 0.9 repeating is a number written in decimal numeral system, and some of the simplest proofs that 0.9 repeating equals 1 rely on the convenient arithmetic properties of this system. Most of decimal arithmetic, addition, subtraction, multiplication, division, and comparison, uses manipulations at the digit level that are much the same as those for integers, and, like integers, any two finite decimals with different digits mean different numbers, ignoring trailing zeros. In particular, any number of the form 0.99 ... 9, where the 9s eventually stop, is strictly less than 1. Unlike the case with integers and finite decimals, other notations can express a single number in multiple ways. For example, using fractions. 1/2 equals 3/6. Infinite decimals, however, can express the same number in, at most, 2 different ways. If there are 2 ways, then one of them must end with an infinite series of 9s, and the other must terminate. That is, consist of a recurring series of zeros from a certain point on. Section 1.1. Fraction Proof. One reason that infinite decimals are a necessary extension of finite decimals is to represent fractions. Using long division, a simple division of integers like 1/3 becomes a recurring decimal, 0.3 repeating, in which the digits repeat without end. This decimal yields a quick proof for 0.9 repeating. Multiplication of 3 times 3 produces 9 in each digit, so 3 times 0.3 repeating equals 0.9 repeating.
but 3 times 1/3 equals 1. So 0.9 repeating equals 1.
Section 1.2, Algebra Proof. Another kind of proof more easily adapts to other repeating decimals. When a number in decimal notation is multiplied by 10, the digits do not change, but the decimal separator moves one place to the right. Thus, 10 times 0.9 repeating equals 9.9 repeating, which is 9 more than the original number. To see this, consider that subtracting 0.9 repeating from 9.9 repeating can proceed digit by digit. The result is 9 minus 9, which is 0, in each of the digits after the decimal separator. But trailing zeros do not change a number, so the difference is exactly 9. The final step uses algebra. Let the decimal number in question, 0.9 repeating, be called C. Then 10C minus C equals 9. This is the same as 9C equals 9. Dividing both sides by 9 completes the proof C equals 1. Section 2, Calculus and Analysis. Since the question of 0.9 repeating does not affect the formal development of mathematics, it can be postponed until one proves the standard theorems of real analysis. Rigorous proofs are generally not studied before the university level.
One requirement is to characterize real numbers that can be written in decimal notation, consisting of an optional sign, a finite sequence of any number of digits forming an integer part, a decimal separator, and a sequence of digits forming a fractional part. For the purpose of discussing 0.9 repeating, the integer part can be summarized as b sub 0, and one can neglect negatives, so a decimal expansion has the form b sub 0, point b sub 1, b sub 2, b sub 3, b sub 4, b sub 5, ... It is vital that the fraction part, unlike the integer part, is not limited to a finite number of digits. This is a positional notation. So, for example, the 5 in 500 contributes 10 times as much as the 5 in 50, and the 5 in 5 100ths contributes 1/10 as much as the 5 in 5/10. Section 2.1, Infinite Series and Sequences. Perhaps the most common development of decimal expansions is to define them as sums of infinite series. In general, b sub 0, point b sub 1, b sub 2, b sub 3, b sub 4, ... equals b sub 0 plus b sub 1 times the quantity 1/10 plus b sub 2 times the quantity 1/10 squared plus b sub 3 times the quantity 1/10 cubed plus b sub 4 times the quantity 1/10 to the 4th power plus ... For 0.9 repeating, one can apply the powerful convergence theorem concerning infinite geometric series. If the absolute value of r is less than 1, then ar plus ar squared plus ar cubed plus ... equals ar divided by 1 minus r. Since 0.9 repeating is such a sum with a common ratio r equals 1/10, the theorem makes short work of the expression 0.9 repeating equals 9 times the quantity 1/10 plus 9 times the quantity 1/10 squared plus 9 times the quantity 1/10 cubed plus ... equals 9 times the quantity 1/10, all divided by 1 minus 1/10, which equals 1.
This proof appears as early as 1770 in Leonard Euler's Elements of Algebra. The sum of a geometric series is itself a result even older than Euler. A typical 18th century derivation used by a term-by-term manipulation similar to the algebra proof given earlier, and as late as 1811, Bonnycastle's textbook An Introduction to Algebra uses such an argument for geometric series to justify the same maneuver on 0.9 repeating.
A 19th century reaction against such liberal summation methods resulted in the definition that still dominates today. The sum of a series is defined to be the limit of the sequence of its partial sums. A corresponding proof of the theorem explicitly computes that sequence. It can be found in any proof-based introduction to calculus or analysis. A sequence, x sub 0, x sub 1, x sub 2, has a limit, x, if the distance, the absolute value of the quantity x minus x sub n, becomes arbitrarily small as n increases. The statement 0.9 repeating equals 1 can itself be interpreted and proven as a limit. 0.9 repeating equals limit n to infinity. 0.9 repeating sub n equals limit n to infinity times the quantity 1 minus 1 divided by 10 to the power of n equals 1 minus limit n to infinity 1 divided by 10n, which equals 1.
The last step, that limit 1 divided by 10 to the power of n equals 0, is often justified by the axiom that the real numbers have the Archimedean property. This limit-based attitude towards 0.9 repeating is often put in more evocative but less precise terms. For example, the 1846 textbook, The University Arithmetic, explains 0.999 plus continued to infinity equals 1, because every annexation of a 9 brings the value closer to 1. The 1895 Arithmetic for Schools says, when a large number of 9s is taken, the difference between 1 and 0.99999 becomes inconceivably small.
Such heuristics are often interpreted by students as implying that 0.9 repeating itself is less than 1. Section 2.2, Nested Intervals and Least Upper Bounds. The series definition above is a simple way to define the real number named by a decimal expansion. A complementary approach is tailored to the opposite process. For a given real number, define the decimal expansions that are to name it. If a real number, x, is known to lie in the closest interval, 0, 10, i.e. it is greater than or equal to 0 and less than or equal to 10, one can imagine dividing that interval into 10 pieces that overlap only at their endpoints. 0, 1, 1, 2, 2, 3, and so on up to 9, 10. The number x must belong to one of these. If it belongs to 3, then one records the digit 2 and subdivides that interval into 2, 2.1, 2.1, 2.2, 2.8, 2.9, 2.93. Continuing this process yields an infinite sequence of nested intervals labeled by an infinite sequence of digits b sub 0, b sub 1, b sub 2, b sub 3, and one writes x equals
b sub 0 point b sub 1, b sub 2, b sub 3,
In this formalism, the fact that 1 equals 1.000 and also 1 equals 0.9 repeating reflects the fact that 1 lies in both 0, 1 and 1, 2, so one can choose either subinterval when finding its digits. To ensure that this notation does not abuse the equals sign, one needs a way to reconstruct a unique real number for each decimal. This can be done with limits, but other constructions continue with the ordering theme. One straightforward choice is the nested intervals theorem, which guarantees that given a sequence of nested, closed intervals whose lengths become arbitrarily small, the intervals contain exactly one real number in their intersection. So, b sub 0 point b sub 1, b sub 2, b sub 3,
is defined to be the unique number contained within all the intervals b sub 0, b sub 0 plus 1, b sub 0 point b sub 1, b sub 0 point b sub 1 plus 1/10, and so on. 0.9 repeating is less than the unique real number that lies in all of the intervals 0, 1, 0.91, 0.991, and 0.99 for every finite string of nines. Since 1 is an element of each of these intervals, 0.9 repeating equals 1. The nested intervals theorem is usually founded upon a more fundamental characteristic of the real numbers, the existence of least upper bounds, or suprema. To directly exploit these objects, one may define b sub 0 point b sub 1, b sub 2, b sub 3 to be the least upper bound of the set of approximants b sub 0, b sub 0 point b sub 1, b sub 0 point b sub 1, b sub 2, One can then show that this definition, or the nested intervals definition, is consistent with the subdivision procedure implying 0.9 repeating equals 1 again. Apostle concludes, the fact that a real number might have two different decimal representations is merely a reflection of the fact that two different sets of real numbers can have the same supremum. Section 3. Skepticism in Education. Students of mathematics often reject the equality of 0.9 repeating and 1 for reasons ranging from their disparate appearance to deep misgivings over the limit concept and disagreements over the nature of infinitesimals. There are many common contributing factors to the confusion. Students are often mentally committed to the notion that a number can be represented in one and only one way by a decimal. Seeing two manifestly different decimals representing the same number appears to be a paradox, which is amplified by the appearance of the seemingly well-understood number 1. Some students interpret 0.9 repeating, or similar notation, as a large but finite string of nines, possibly with a variable, unspecified length. If they accept an infinite string of nines, they may still expect a last 9 at infinity. Intuition and ambiguous teaching lead students to think of the limit of a sequence as a kind of infinite process rather than a fixed value, since the sequence never reaches its limit. Those who accept the difference between a sequence of numbers and its limit might read 0.9 repeating as meaning the former rather than the latter. These ideas are mistaken in the context of standard real numbers. Although many of them are partially borne out in more sophisticated structures, either invented for their general mathematical utility or as instructive counterexamples to better understand 0.9 repeating. Many of these explanations were found by Professor David Tull, who has studied characteristics of teaching and cognition that lead to some of the misunderstandings he has encountered in his college students. Interviewing his students to determine why the vast majority initially rejected the equality, he found that students continued to conceive of 0.9 repeating as a sequence of numbers getting closer and closer to 1 and not a fixed value, because you haven't specified how many places there are, or it is the nearest possible decimal below 1. Of the elementary proofs, multiplying 0.3 repeating equals 1/3 by 3 is apparently a successful strategy for convincing reluctant students that 0.9 repeating equals 1. Still, when confronted with the conflict between their belief of the first equation and their disbelief of the second, some students either begin to disbelieve the first equation or simply become frustrated. Nor are more sophisticated methods foolproof. Students who are fully capable of applying rigorous definitions may still fall back on intuitive images when they are surprised by a result in advanced mathematics, including 0.9 repeating.
For example, one real analysis student was able to prove that 0.3 repeating equals 1/3 using a supremum definition, but then insisted that 0.9 repeating was less than 1 based on her earlier understanding of long division. Joseph Mazur tells the tale of an otherwise brilliant calculus student who challenged almost everything I said in class but never questioned his calculator, and who had come to believe that 9 digits are all one needs to do mathematics, including calculate the square root of 23.
The student remained uncomfortable with a limiting argument that 9.9 repeating equals 10, calling it a widely imagined infinite growing process.
As part of Ed Dubinsky's APIS theory of mathematical learning, Dubinsky and his collaborators proposed that students who conceive of 0.9 repeating as a finite, indeterminate string with an infinitely small distance from 1 have not yet constructed a complete process conception of the infinite decimal. Other students who have a complete process conception of 0.9 repeating may not yet be able to encapsulate that process into an object conception like the object conception they have of 1. And so they view the process 0.9 repeating and the object 1 as incompatible. Dubinsky et al. Also link this mental ability of encapsulation to viewing 1/3 as a number in its own right and to dealing with the set of natural numbers as a whole.
Section 4. The real numbers. Other approaches explicitly define real numbers to be certain structures built upon the rational numbers using axiomatic set theory. The natural numbers, 0, 1, 2, 3, and so on, begin with 0 and continue upwards, so that every number has a successor. One can extend the natural numbers with their negatives to give all the integers, and to further extend to ratios, giving the rational numbers. These number systems are accompanied by the arithmetic of addition, subtraction, multiplication, and division. More subtly, they include ordering, so that one number can be compared to another and found less than, greater than, or equal. Two numbers, which are now sets, are equal if and only if they have the same elements. The step from rationals to reals is a huge extension, and there are at least two popular ways to achieve this step, both published in 1872. Dedekind cuts and Cauchy sequences. Proofs that 0.9 repeating equals 1 that directly use these constructions are not found in textbooks on real analysis, where the modern trend for the last few decades has been to use an axiomatic analysis. Even when a construction is offered, it is usually applied towards proving the axioms of the real numbers, which then support the above proofs. However, several authors express the idea that starting with a construction is more logically appropriate and the resulting proofs are more self-contained. The following two examples come from rather unique sources. Section 4.1, Dedekind cuts. In the Dedekind cut approach, each real number x is the infinite set of all rational numbers that are less than x. In particular, the real number 1 is the set of all rational numbers that are less than 1. Every positive decimal expansion easily determines a Dedekind cut, the set of rational numbers which are less than some stage of the expansion. So the real number 0.9 repeating is the set of rational numbers r such that r is less than 0, or r is less than 9/10, or r is less than 99/100, or r is less than some other number in the form 1 minus the quantity 1/10 to the power of n. Since 0.9 repeating and 1 contain the same rational numbers, they are the same set, 0.9 repeating equals 1. The definition of real numbers as Dedekind cuts was first published by Richard Dedekind in 1872. The approach to assigning a real number to each decimal expansion is due to an expository paper entitled, Is 0.9 repeating equal to 1? by Fred Richman in Mathematics Magazine, which is targeted at undergraduate mathematicians. Richman notes that taking Dedekind cuts in any dense subset of the rational numbers yields the same results. In particular, he uses decimal fractions, for which the proof is more immediate. So we see that in the traditional definition of the real numbers, the equation 0.9 equals 1 is built in at the beginning. A further modification of the procedure leads to a different structure that Richman is more interested in describing. Section 4.2. Cauchy sequences. Another approach to constructing the real numbers uses the ordering of rationals less directly. First, the distance between x and y is defined as the absolute value of the quantity x minus y, where the absolute value of z, is defined as the maximum speed of z and the opposite of z, thus never negative. Then the reals are defined to be the sequences of rationals that are Cauchy using this distance. That is, in the sequence x sub 0, x sub 1, x sub 2, ... a mapping from natural numbers to rationals. For any positive rational delta, there is an n such that the absolute value of the quantity x sub m minus x sub n is less than or equal to delta for all m n is greater than n. The distance between terms becomes arbitrarily small. If x sub n and y sub n are two Cauchy sequences, then they are defined to be equal as real numbers if the sequence x sub n minus y sub n has the limit 0. Truncations of the decimal number b sub 0, point b sub 1, b sub 2, b sub 3, ... generate a sequence of rationals which is Cauchy. This is taken to define the real value of the number. Thus, in this formalism, the task is to show that the sequence of rational numbers 1 minus 0, 1 minus 9/10, 1 minus 99 100ths, ... equals 1, 1/10, 1 100th, ... has the limit 0, considering the nth term of the sequence. For n equals 0, 1, 2, ... it must therefore be shown that limit n to infinity 1 over 10 to the nth power equals 0. The definition of real numbers as Cauchy sequences was first published separately by Edward Hein and Georg Cantor, also in 1872. The prior approach to decimal expansions, including the proof that 0.9 repeating equals 1, closely follows Griffiths and Hilton's 1970 work, A Comprehensive Textbook of Classical Mathematics, a Contemporary Interpretation. The book is written specifically to offer a second look at familiar concepts in a contemporary light. Section 5. Other number systems. Although the real numbers form an extremely useful number system, the decision to interpret the phrase 0.9 repeating as naming a real number is ultimately a convention, and Timothy Gowers argues in Mathematics, a very short introduction, that the resulting identity 0.9 repeating is equal to 1 is a convention as well. However, it is by no means an arbitrary convention, because not adopting it forces one either to invent strange new objects or to abandon some of the familiar rules of arithmetic. One can place constraints on hypothetical number systems where 0.9 repeating is not equal to 1 with their new objects or unfamiliar rules, or both, by reinterpreting the previous proofs. As Richman puts it, one man's proof is another man's reductio ad absurdum. If 0.9 repeating is to be different from 1, then at least one of the assumptions built into the proofs must break down. Section 5.1. Infinitesimals. Some proofs that 0.9 repeating equals 1 rely on the Archimedean property of the standard real numbers. There are no non-zero infinitesimals. There are mathematically coherent ordered algebraic structures, including various alternatives to standard reals, which are non-Archimedean. For example, the dual numbers include a new infinitesimal element e, analogous to the imaginary unit I in the complex numbers, except that e squared equals 0. The resulting structure is useful in automatic differentiation. The dual numbers can be given a lexicographic order, in which case the multiples of e become non-Archimedean elements. Another way to construct alternatives to standard reals is to use topos theory and alternative logics rather than set theory and classical logic. For example, smooth infinitesimal analysis has infinitesimals with no reciprocals. Non-standard analysis is well known for including a number system with a full array of infinitesimals and their inverses, which provide a different and perhaps more intuitive approach to calculus. A. H. Lightstone provided a development of non-standard decimal expansions in 1972, in which every extended real number in 0, 1 has a unique extended decimal expansion, a sequence of digits 0.ddd indexed by the extended natural numbers. In his formalism, there are two natural extensions of 0.3 repeating, neither of which falls short of 1/3 by an infinitesimal. 0.333 ... 000 ... does not exist, while 0.333 ... 333 ... equals exactly 1/3. Combinatorial game theory provides alternative reals as well, with infinite blue-red Hackenbush as one particularly relevant example. In 1974, Elwin Berkelkamp described a correspondence between Hackenbush strings and binary expansions of real numbers motivated by the idea of data compression. For example, the value of the Hackenbush string LRR is 0.010101 ... which equals 1/3. However, the value of LRLLL ... corresponding to 0.111 ... is infinitesimally less than 1. The difference between the two is the surreal number 1-W, where W is the first infinite ordinal. The relevant game is LRRRR ... or 0.000 ... Section 5.2. Breaking subtraction. Another way that the proofs might be undermined is if 1 minus 0.9 repeating simply does not exist because subtraction is not always possible. Mathematical structures with an addition operation but not a subtraction operation include commutative semigroups, commutative monoids, and semirings. Richmond considers two such systems designed so that 0.9 repeating is less than 1. First, Richmond defines a non-negative decimal number to be nothing more or less than a literal decimal expansion. He defines a lexicographical order and an addition operation, noting that 0.9 repeating is less than 1, simply because 0 is less than 1 in the ones place. But for any non-terminating x, 1 has 0.9 repeating plus x equals 1 plus x. So, one peculiarity of the decimal numbers is that the addition cannot always be cancelled. Another is that no decimal number corresponds to 1/3. After defining multiplication, the decimal numbers form a positive, totally ordered, commutative semiring. During the definition of multiplication, Richmond defines another system he calls cut D, which is a set of Dedekind cuts of decimal fractions. Ordinarily, this definition leads to the real numbers, but for a decimal fraction d, he allows both the cut, the opposite of infinity, d, and the principal cut, the opposite of infinity, d. The result is that the real numbers are living uneasily together with the decimal fractions. Again, 0.9 repeating is less than 1. There are no positive infinitesimals in cut d, but there is a sort of negative infinitesimal, 0 negative, which has no decimal expansion. He concludes that 0.9 repeating is equal to 1 plus 0 negative, while the equation 0.9 repeating plus x equals 1 has no solution. Section 5.3, p-adic numbers. When asked what 1 minus 0.999 might be, students often invent the number 0.000 ... Whether or not that makes sense, the intuitive goal is clear. Adding a 1 to the last 9 in 0.999 ... would carry all the 9's into zeros and leave a 1 in the 1's place. Among other reasons, this idea fails because there is no last 9 in 0.999 ... For an infinite string of 9's, including a last 9, one must look elsewhere. The p-adic numbers are an alternate number system of interest in number theory. Like the real numbers, the p-adic numbers can be built from the rational numbers via Cauchy sequences. The construction uses a different metric in which 0 is closer to p and much closer to p to the power of n than it is to 1. The p-adic numbers form a field for prime p and a ring for other p, including 10. So arithmetic can be performed in the p-adics, and there are no infinitesimals. In the 10-adic numbers, the analogues of decimal expansions run to the left. The 10-adic expansion ... 999 does have a last 9, and it does not have a first 9. One can add 1 to the 1's place, and it leaves behind only zeros after carrying through. 1 plus ... 999 equals ... 000 equals 0, and so ... 999 equals -1. Another derivation uses a geometric series. The infinite series implied by ... 999 does not converge in the real numbers, but it converges in the 10-adics, and so one can reuse the familiar formula ... 999 equals 9 plus 9 times 10 plus 9 times 10 squared plus 9 times 10 cubed plus ... equals 9 over the quantity 1 minus 10, which equals -1. A third derivation was invented by a 7th grader who was doubtful of her teacher's limiting argument that 0.9 repeated equals 1, but was inspired to take the multiply by 10 proof in the opposite direction. If x equals ... 999, then 10x equals x minus 9, hence x equals -1 again. As a final extension, since 0.9 repeating equals 1, and ... 999 equals -1, then by blind faith and unabashed juggling of symbols, one may add the two equations and arrive at ... 999.9 repeating equals 0. This equation does not make sense either as a 10-adic expansion or an ordinary decimal expansion, but it turns out to be meaningful and true if one develops a theory of double decimals with eventually repeating left ends to represent a familiar system, the real numbers. Section 6, Generalizations. Proofs that 0.9 repeating equals 1 immediately generalize in two ways. First, every non-zero number with a finite decimal notation, equivalently endless trailing zeros, has a doppelganger with trailing 9's. For example, 0.24999 ... equals 0.25, exactly as in the special case considered. These numbers are exactly the decimal fractions, and they are dense. Second, a comparable theorem applies in each radix or base. For example, in base 2, the binary numeral system, 0.1 repeating equals 1, and in base 3, the ternary numeral system, 0.2 repeating equals 1. Textbooks of real analyses are likely to skip the example of 0.9 repeating and present one or both of these generalizations from the start. Alternate representations of 1 also occur in non-integer bases. For example, in the golden ratio base, the two standard representations are 1.000 ... and 0.101010 ... and there are infinitely many more representations that include adjacent ones. Generally, for almost all q between 1 and 2, there are uncountably many base q expansions of 1. On the other hand, there are still uncountably many q, including 2 and 10, for which there is only one base q expansion of 1, other than the trivial 1.000 ... This result was first obtained by Paul Erdos, Miklos Horvath, and Istvan Joe around 1990. In 1998, Vilmos Komornik and Paula Loretti determined the smallest such base, q equals 1.7872311650 ... In this base, 1 equals 0.1100100100110011001100110011. The digits are given by the Thue-Morse sequence, which does not repeat. A more far-reaching generalization addresses the most general positional numeral systems. They too have multiple representations, and in some sense the difficulties are even worse. For example, in the balanced ternary system, 1/2 equals 0.111 ... which equals 1.111 ... In the factoratic system, 1 equals 1.000 ... which equals 0.1234 ... Marko Petkovsek has proved that such ambiguities are necessary consequences of using a positional system. For any system that names all the real numbers, the set of reals with multiple representations is always dense. He calls the proof an instructive exercise in elementary point set topology. It involves viewing sets of positional values as stone spaces and noticing that their real representations are given by continuous functions. Section 7. Applications. One application of 0.9 repeating as a representation of 1 occurs in elementary number theory. In 1802, H. Goodwin published an observation on the appearance of 9s in the repeating decimal representation of fractions whose denominators are certain prime numbers. Examples include 1/7, which equals 0.142857142857 ... and 142 plus 857 equals 999. And 1/73, which equals 0.0136986301369863 ... and 136 plus 9863 equals 9999. E. Mitty proved a general result about such fractions, now called Mitty's theorem, in 1836. The publication was obscure, and it is unclear if his proof directly involved 0.9 repeating, but at least one modern proof by W. G. Levitt does. If one can prove that a decimal of the form 0.b1, b2, b3 ... is a positive integer, then it must be 0.9 repeating, which is then the source of the 9s in the theorem. Investigations in this direction can motivate such concepts as greatest common divisors, modular arithmetic, Fermat primes, order of group elements, and quadratic reciprocity. Returning to real analysis, the base 3 analog 0.222 ... equals 1 plays a key role in a characterization of one of the simplest fractals, the middle thirds Cantor set. A point in the unit interval lies in the Cantor set if and only if it can be represented in ternary using only the digits 0 and 2. The nth digit of the representation reflects the position of the point in the nth stage of the construction. For example, the point 2/3 is given the usual representation of 0.2 or 0.2000 ... since it lies to the right of the first deletion and to the left of every deletion thereafter. The point 1/3 is represented not as 0.1, but as 0.0222 ... since it lies to the left of the first deletion and to the right of every deletion thereafter. Repeating 9s also turn up in yet another of Greg Cantor's works. They must be taken into account to construct a valid proof applying his 1891 diagonal argument to decimal expansions of the unaccountability of the unit interval. Such a proof needs to be able to declare certain parts of real numbers to be different based on their decimal expansions, so one needs to avoid pairs like 0.2 and 0.1999... A simple method represents all numbers with non-terminating expansions. The opposite method rules out repeating nines. A variant that may be closer to Cantor's original argument actually uses base 2, and by turning base 3 expansions into base 2 expansions, one can prove the uncountability of the Cantor set as well. Section 7. In popular culture. With the rise of the Internet, debates about 0.9 repeating have escaped the classroom and are commonplace on news groups and message boards, including many that nominally have little to do with mathematics. In the newsgroup SCI.math, arguing over 0.9 repeating is a popular sport, and it is one of the questions answered in its frequently asked questions. The frequently asked questions briefly covers 1/3, multiplication by 10, and limits, and it alludes to Cauchy sequences as well. A 2003 edition of the general interest newspaper column The Straight Dope discusses 0.9 repeating via 1/3 and limits, saying of misconceptions, "The lower primate in us still resists, saying 0.999 doesn't really represent a number, then but a process. To find a number, we have to halt the process, at which point the 0.999 equals one thing falls apart. Nonsense." The Straight Dope cites a discussion on its own message board that grew out of an unidentified other message board, mostly about video games. In the same vein, the question of 0.9 repeating proved such a popular topic in the first 7 years of Blizzard Entertainment's Battle.net forums that the company's president, Mike Morhaime, announced at an April 1, 2004 press conference that it is won. We are very excited to close the book on this subject once and for all. We've witnessed the heartache and concern over whether 0.999 does or does not equal 1, and we're proud that the following proof finally and conclusively addresses the issue for our customers. Blizzard's subsequent press release offers 2 proofs based on limits and multiplication by 10. Section 9. Related questions. Zeno's paradoxes, particularly the runner paradox, are reminiscent of the apparent paradox that 0.9 repeating and 1 are equal. The runner paradox can be mathematically modeled and then, like 0.9 repeating, resolved using the geometric series. However, it is not clear if this mathematical treatment addresses the underlying metaphysical issues Zeno was after. Division by 0 occurs in some popular discussions of 0.9 repeating, and it also stirs up contention. While most authors choose to define 0.9 repeating, almost all modern treatments leave division by 0 undefined, as it can be given no meaning in the standard real numbers. In other systems, such as the Riemann sphere, it makes sense to define 1 divided by 0 to be infinity. In fact, some prominent mathematicians argued for such definition long before either number system was developed. Negative 0 is another redundant feature of many ways of writing numbers. In number systems, such as the real numbers, where 0 denotes the additive identity and is neither positive nor negative, the usual interpretation of negative 0 is that it should denote the additive inverse of 0, which forces negative 0 equals 0. Nonetheless, some scientific applications use separate positive and negative zeros, as do some of the most common computer number systems. For example, the IEEE floating point standard. This article belongs in the categories Mathematics Paradoxes, Real Analysis, Real Numbers, Numeration, and Proofs.